Hi, and welcome to this new video on the series Introduction to Parametric Modeling, where we're going to do a hands-on exercise, still practicing lists and still practicing ways of manipulating data for creating geometry. And in this one, we're going to do a super cool exercise, which is going to be modeling a spatial truss that is going to have an internal triangulation that is going to follow the Warren pattern. The Warren pattern is a pattern that looks something like this. This is the Warren truss, but we have chosen to do it in 3D inspired by some examples of, for example, the canopies of airports that typically display this pattern. So it's going to be super interesting. We're going to imagine that we're going to design some kind of like really structural canopy that has a lot of span and that it needs this really strong structure sustaining it. Of course, everything is going to be parametric, so the height of the arch, the depth of the truss, the width of the truss, and we're going to start from points that are going to be defined. The supports are going to be defined as points. And we will end up by doing a few modifications so that we can also not just apply this to two single supports, but apply this logic to a full two full collections of supports, so that we can generate this kind of pavilion looking kind of design that has all the 3D spatial structures on top of it, and which, if we actually bake, it will look something like this, which I find like a super interesting kind of exercise. We're going to learn techniques for this exercise, such as weaving data. We're going to learn techniques such as culling data. So if you've been following this series, we're going to learn a few new components that we haven't seen before. And it's going to be super fun, and it's not going to be that complicated to get this really powerful result. So join me in this journey of designing 3D spatial structures, and hopefully we will learn a lot of stuff together. Let's get hands-on. Wonderful. So let's get started. How are we going to approach this? Well, as we saw on the diagram, we're going to create these spatial structures that are going to be spanning a very large distance on top of two supports, and they're going to have basically a kind of triangular section of sorts, and they're going to have a triangulation of bars that is going to be following more or less that Warren logic that we spoke of. So what we're going to do is, I think we're going to divide this exercise in two main parts. The first one is going to be creating the basic geometry, so creating the two supports and then creating the three main bars, like long bars that join them, the triangulated section. And then a second stage will be creating the internal triangulation inside of the truss to give it stiffness, to give it stability. And for the first one, and for the first stage, we're actually going to do it a little faster because it's like basic simple geometry manipulations. It's things that we are already a little familiar at this point in this playlist. So we're going to do a simple process where we're going to start with two supports, which are probably going to be points in Rhino because we like the fluidity of moving things in Rhino, etc. Then we're going to create some kind of NURBS curves that is going to join them like that. And then we're going to create another two NURBS curves on top of it, which in a way somehow are going to create this triangular section among them. And then probably the parameters that I will want to control here are going to be the following. I will probably want to control the length of between the spans, which is not going to be direct. It's going to be, as we said, implicit based on where the 2 points are. Then we probably want to control the base height of the arch, so the main opening that is going to the main height of the arch, right? We will want to control small things such as the depth and the width of the triangulation at the center of the beam. And for these three elements, for the height, for the depth, and for the width, I think I will want them, except maybe the width, I'm not sure about that. I will want to, instead of having them as straight values, I would like to have them as factors of the length, so that whenever the length is smaller, the height is smaller, and also the depth of the beam is smaller as well, so that we get a more optimized beam, a more optimized truss, as we saw on the previous exercises. So I think I'm going to go ahead and do this, and perhaps I'm going to do it a little faster than usual so that we can get this done as soon as possible, and then we can start dealing with the more complicated part, perhaps, which is going to be designing the internal triangulation of bars that is going to be inside of the truss. Let's get started with this. Okay, to speed things up, I have gone ahead and started the grasshopper definition. As usual, I have 2 points in Rhino that I brought here as empty boxes in Grasshopper, and I have a few sliders that I have customized to be the height of the beam. And look at what I'm doing here. I am just annotating myself here that this height is not going to be an absolute value in units. It's going to be whatever the length between those 2 points will be divided by this number. This is just my internal annotation. And same for the depth. The depth will be whatever the length of between the 2 supports divided by this number, and the width will be L divided by this number. So the 3 factors are going to be factors of the length. And then what I'm going to do is I now need to create the 3 main arches. I'm going to follow a very simple logic, which is going to be, if I am here, so my logic is going to be that I'm going to create, I have the 2 supports, I'm going to create a line between them, find the point in the middle, I'm going to move that point like a controlled amount of distance in the z direction, which is going to be h, and then that point, I will move it up a controlled distance here, which is going to be the depth, and I will move it in the 2 directions, like half the width and half the width, so that I can create the 2 points here, so that I can create an arch between these 3 points, another arch between these 3 points, and another arch between these 3 points. And those are going to be the 3 main arches that I will use in the rest of the definition for calculating all the bars and all the structure inside of the truss. So let's get started. So very simple. I'm going to group this because these are my inputs, and then I'm going to create a line between 2 points, a bit between the start point and the end point, and then I would like to find a point at the center of that line. So what I can do is I can go to curve analysis, and I can find, for example, I can evaluate the curve. What is evaluate the curve? I can evaluate the curve so that I can find at a specified parameter, I can specify points, tangents, and angle. Because I know that a line, by definition, has a domain that goes from 0 to 1. I know that the center point will be exactly at the parameter 0.5. This rule only works for straight line segments. It doesn't work like this for curves. Okay, remember that, please. And now we have evaluate curve. So this is the point, and then I just need to move that point in the z direction. I just need to move that point in the z direction, a control amount that is going to be equal to the height. But the height is a factor of the length between the 2 points. So remember that I need to take this and I need to calculate the length between the 2 points. So that's going to be the length of this segment. All right. Or alternatively, I could also do this. We haven't seen this yet. I could also do this by calculating the distance between 2 points. So if I go to vector, point, and distance, you can see that here I can compute the Euclidean distance between 2 point coordinates. And that is going to be the starting point and the end point. And that will give me d, which is a linear distance between them. If I now divide that distance, division, by the truss height, this will give me the actual height of the truss. And actually, sorry, I'm going to just move things around a little bit, and I'm going to add myself a number here. Sorry, this is not a number. I'm going to add myself a number here to remind me that this is the actual height, not not the factor, but the actual numerical height that I will probably be using along a lot farther down the road. So I would like to now copy and paste this 3 times, because the depth will be a factor of this and the width will also be a factor of this. And so this will be the depth, this will be the depth, and this will be the width of the beam. And I'm going to group this as in these are the actual calculations for the height, the depth, and the truss of the beam, so that I have them, the 3 numbers here, and that I know where to drag from as far as as much as I continue developing my definition. So as I was saying, I have my point here. I want to move it up. I control amount z, and which is going to be equal to the height, this value that I've already computed. So I plug that in here, and then I can now create, for example, an interpolated curve, which is going to go from the start point, the start support, to this point in the middle that I generated. So I plug in by pressing shift so that they both go in together. And then the third point is going to be the end point. So I also shift add it here. Correct? And this is going to be the main, this is going to be the base arch of my truss, which is going to be somewhere here. And if I want to name this, I can drop an empty curve box. This is going to be the base arch, and I can click on the paint bucket to give it the name here. Okay, wonderful. So this is how we do the base arch. So now let's do the other 2 additional arches. If you remember from our diagrams, well, the only thing we need to do is we need to take the base point, which is here, and we need to move it up and to the left and up and to the right, controlled distances, which are the depth of the truss and half the width on each direction. So let's see how can we do that. So we have the point here. This is the point on top of the arch. So we're going to first figure out how to move it in the z direction. The z direction is going to be just as simple as taking another z vector that is factor or multiplied by the depth in the vertical direction. And then we can take, for example, we can take this point, the point that we did, and we can just move it up by that factor, and we just have it there, right? Now, what we need to do now is we need to move this point in half the width in one direction and half the width in the other direction. However, technically speaking, we don't really have anywhere, we don't really have a vector that is pointing perpendicular to the plane that is formed by the starting support, the middle point in the arch, and the end support. We don't really have that vector anywhere. So there are 2 ways that we can go about this. We can either create a vector in this direction and then take that vector and rotate it around z 90 degrees. That can be one way to go, but I'm not sure that I like that one a lot. I think I like better to just say, why don't we create a plane that is containing this point, and this point. So something like this, a plane that is, the origin is here, the main vector is pointing in the direction of the other support, and we use the third point to take the second to define the secondary axis. And then what that will give us is a plane whose normal, the normal vector, is going to be perpendicular to that arch. And therefore, if we use those 3 points, then we know that that vector will always be perpendicular no matter of where the 3 points are in 3D space, which is something that the previous technique may not address very well. So I think we're going to do that. So we're going to do that, and we're going to say, let me create a plane defined by 3 points. So I'm going to go to vector, plane, and I'm going to create a plane defined by 3 points. Which are those 3 points going to be? The first one is going to be the starting point. So that's going to be the start support here. The second one is going to be pointing to this point here, which is the second support. So that's going to be the end support. And then the third point is going to be a point that is going to be the one that we just defined before. And therefore, look how nice this is. We have a plane now that is centered here, that is oriented towards the other support, and whose secondary axis is pointing upwards and is containing the arch, which is a planar curve. The normal to this plane will be a vector that is perpendicular to this plane. So let me extract that normal by deconstructing the plane and, for example, visualizing that vector with a vector display. So I'm going to visualize the vector here, and the vector that I want to visualize is this one here. So you see, this vector is now pointing outwards from the plane of the truss. So if I now take that vector and set its length to be half the width, then I can multiply that by 1 or by minus 1, and that can be the vector that I use to move this point in this direction and this direction. So let's do that. So I'm going to calculate here. On one end, I'm going to calculate with an expression. I'm going to type, this is going to be W, and then what I want to calculate here is W divided by 2, that's going to be 1. And then the other one is going to be minus W divided by 2. And then because I have the width here, I'm going to plug these two here, 1 and 2. And then I'm going to multiply the normal vector C. I'm going to multiply it by this expression. So I'm going to multiply it by this length. And I'm also going to multiply it by this other length. And I'm going to visualize that here. I'm going to visualize it here. That's one. And then that's also the other one. But if I want to visualize them on top here, I can also visualize them there. All right. And then just like I have added, what I can do is I can add the C vector with the depth and the C vector with the width. I can add them together to create, for example, let me add the vector that is going to move this point up. Let me add that vector to the vector that is moving it in the left direction. If I now showcase that vector, you can see that it's a vector that is pointing sideways out of the plane. And if I now do the same with the other vector here, you can see that as I add it here, I have the two vectors that are moving this point in the triangular form. And then as I do that, I can just move the original point by this vector, and now move the original point by the other vector. And I can turn this off, and I can see that I now have the three main points for each one of the arches. And then what I can do now is I can say, well, this is going to be one thing, and then this is going to be the main arch, and this is going to be here. I can copy and say, I'm going to create an interpolated curve. I'm going to disconnect everything just to make sure that I do it right. Between the start point, the new middle point I have created with a shift, and the end point, the end support. And then I'm going to create another interpolated curve. I'm going to copy and paste. I'm going to right click here and disconnect everything. And then I'm going to plug in the first support. I'm going to plug in the middle point with the shift, and then I'm going to plug in the end support. And you can see that I have the three arches, each one of them with the base one, and then the two on the top with the opening. And if I control things here, you can see that this is now adapting. this is also, the depth is also adapting, and the width is also adapting. And it also adapts because if I bring the points closer to each other, everything opens up proportionally. So I'm going to now turn off a bunch of geometry that is kind of temporary, like this one and this one and this one. And I'm going to make sure that I end up with the clean 3 boxes. Top left, for example, top left arch. And this is going to be top right arch. And I'm going to move them here, and I'm going to create a group to make sure that they are very clearly identifiable. I'm going to turn off the plane as well, and then this middle point here. And now, very cleanly, I have those 3 curves, those 3 arches that are joining the 2 support points. And all of this, I can probably now just create a group here, and then create another group here, and then I would label this, blah, blah, blah. But I know that anything that is happening here in the middle, I don't need to care about anymore, because what's important is that I have been able to generate those 3 curves, the base, the top left, and the top right. Okay? So at this point, I think I'm ready now to start working on creating the triangulation inside of the truss. Let's take a look at how to do that. As usual, thinking by drawing or by sketching is, I think, is one of the most useful ways of thinking through problems. So let me explain how I think we're going to approach this problem. What we have is an arch that is the base of the truss, and we have 2 other curves that are the top of the arch. And for the sake of this diagram, we're going to assume that the top one is the same. It's just the 2. We're not going to take care of that. And then what we're going to do is, in order to start generating bars that generate the internal triangulation of the truss, we probably want to do something where we subdivide each one of the curves in a regular amount of points, in a controlled amount of spans, right? But then, if we just took all of those points and we started joining them with bars, the way we've done in previous exercises, because of this particular truss in 3D space, because it kind of has this shape that starts as in one point and then it opens up and then it closes down, if we were to just generate triangulations like that, we would probably end up with something like this, where I'm not sure if you can see, but here on the ends, these bars look kind of weird. And if this opening is not big enough, these bars may also be kind of like they're like a little bit in the way. So it's actually very common that in these kind of special structures, there is like a gap, typically a large gap here before you start actually doing the triangulation. So I would like to propose that we also do that, which is just involves a little bit of data manipulation. And if we say, for example, that if we said that this, for example, if we said that this truss needs to have, for example, 8 spans or 8 gaps between them, which is the total amount, we may also want to define another variable that is going to be, for example, the number of void gaps or void spans at the ends of the truss, which in this case, for this diagram that I'm drawing, could be 2, so that I have 1 and 2 spans that are empty, they don't have triangulation, and then I have another 2 spans that don't have triangulation, but the total is 1, 2, 3, 4, 5, 5, 6, 7, and 8. Okay? So what we will do is we will calculate the total amount of spans, but then we will subtract, we will remove only, we will remove points at the ends of those collections so that we only do triangulations at the center. Now, something that we probably will want to do after that is extract from those 2 collections the points that I'm going to do triangulations on. And again, this will involve figuring out how many gaps, how many empty gaps do I have on the sides. And And also something that I could do is I could arguably say I'm just going to take these two collections, or because I know that the triangulation is in a worn way, I may want to just take the one here in the bottom. Maybe, I don't know, without the other ones. So I think that for symmetry and also for showing a little bit of the other techniques that I want to teach you, in this case, in this particular exercise, we're going to take the same amount of points from the top and from the bottom arches. But arguably, you could decide to just design this algorithm in a different way. It's not a bad thing. And then after we have that, what we will end up with is with a subset of points that are ordered in this particular way. So the top points and the bottom points. I could use techniques similar to the techniques that I have used in the previous exercises. What I now can go and say, well, I want to now draw this bar and this bar, all the ones that are to the left, and then on a separate process, I'm going to do the ones that are to the right and to the right. This could be a way to go. But since we've already learned how to do that, I kind of want to teach you different techniques, different techniques now. So what I would like to propose is that for this particular exercise, we follow a different technique. And the different technique is that since this exercise is maybe not so much designed for structural calculation, but is more for the design of an airport canopy or whatever, in this case, what I would like to propose is that instead of generating individual bars, what we do is we create one continuous polyline between all those points, that we generate a continuous polyline between these points, between the first point here, the second point here, the third point here, fourth point, and the fifth point. And then if we need to explode that polyline into individual segments, we can do it at a second process. But the result will be a polyline that will do something like that. So for that, we will actually need to do some kind of geometry processing or list processing that will involve creating a new line that has element number 0 from the top, element number 1 from the bottom, element number 2 from the top, element number 3 from the bottom, element number 4 from the top. And that process is going to involve doing two operations that we haven't seen on the lectures, but that I will teach you through this exercise, which are going to be culling. So that will involve removing this element and this element from the top one, and this element and this element and this element from the bottom one. So cherry picking, how to remove elements with a pattern, and then weaving, which will be creating a list that instead of having all these elements and then all these elements afterwards, which is what we know how to do now, we'll have this element weaved with this second one, weaved with this third one, fourth one, in this particular arrangement that I have defined here. Are you excited and ready to do this? I think it's about time that we give it a try. Let's take a look at how to do this in Grasshopper. So back in Grasshopper, I have created two sliders. One is the total amount of spans, as we discussed in the diagram, and the other one is going to be the number of void spans that we're going to have on each side of the truss. And I will use those numbers to do my data manipulation, my data list manipulation. So what are we going to do now? So what I'm going to do is I'm going to take the base arch and I'm going to divide into a bunch of spans. Okay, how many segments am I going to divide it? The amount of spans that I have defined here on the number of spans that I have defined on my inputs. So that's going to look something like that. And I'm going to do the same thing for the top left arch. And just to keep things a little clean, I'm going to kind of forget about the other one for the time being. So because the other one is basically going to be copy pasted from the left one. So I'm just going to work with one of the ones above. So what I need to do now is I have all these points, so all the points in the bottom and all the points in the top. And what I need to do is I need to extract the families that are going to be at the center after I remove the gaps on each side. So what I need to do is, if I'm about to do this in a clean way, the way to do about that is by defining here extracting from the list of curves just a subset of extracting just a subset of those points. What is the domain that I need to extract going to be? You know me already. I like thinking through drawing, so let's take a closer look. So if we imagine that we have a situation where the number of spans is 8 and the number of voids on each side is 2. So what we would want to do is we would want to extract this family of points from that list. And if the points are numbered like this from 0 to 8, because there's 9 points, remember there's 8 spans, so that means there's 9 points. So what I probably want to do is I want to create a domain where I extract from this element, whatever its index number is, to this element, whatever its index number is. And it turns out that the first one, this one, is going to be equal to V, to the amount of spans that we have on each side, the amount of empty ones. And it turns out that this one here, the last one, is going to be equal to the amount of total spans minus the amount of empty spans on each side. So if you see here, 6 is going to be equal to 8 minus 2, correct? So it's going to be a very simple numerical rule about creating a domain that we're going to use to extract this sub list of points from the total on the top arch, and the same for the bottom arch. So let's just do that. I'm going to click here and I'm going to construct a domain, and then I'm going to move the sublist here, and then the start of the domain is going to be equal to this parameter, so how many void spans, so that's going to be the number 2. So that's going to be the start, and the end, as we said in the diagram, is going to be the amount of spans minus the amount of void spans. So that is going to be super easy. So I'm just going to create a subtraction here. I'm going to subtract from the total amount of spans. I'm going to subtract the amount of void spans. And that is what I'm going to use for this end of the domain. If I do that, if I plug that domain in here, you can see that when I click, this point turn on, and let me see if this works. So if I add many more spans, yes, it is true that there's always 2 empty ones here, but if I increase this, you can see how I start getting more empty spans on each side. So I think this is working correctly so far. So we are going to use that for creating the sublist also from the points on the top arch. So that's going to be the points, and this is going to be the same domain. Okay, and I'm going to turn this off, and then you can see how now we are left with the points in the bottom and the points in the top. And as I typically do, because we're going to start getting, it's going to start getting messy with lists and combinations, whatever, I would like to have the point list component here nearby to make sure that I have a good control over what's going on. Okay? All right, so what is next? If we go back to the diagram, what we need to do now is from each one of the families of points, the top and the bottom, so from this one, we need to basically remove every other point from the list. So from this one, I basically want to remove this one, and keep this one, and keep this one, and keep this one. And from the bottom one, I want to remove this one, and this one, and just keep this one and this one. So I need to take the 2 lists that I just generated and use a process called culling to apply a pattern of yes and no to which points do I want to keep and which points do I want to remove from that list. With the techniques that we have seen so far, there aren't any operations that do this on the list. So let me show you a component that we can use to do that. That component is going to be here under sequences, and what we can do is, for example, we can call or we can remove elements in a list by using a mask, by using a pattern. What does that look like? So I'm going to plug my points here. I'm going to work on the ones on the bottom, and you can see that the call pattern component takes the list that you want to call, and then a pattern which is a list of truths and falses. A list of truths and falses about which points get to stay and which points get to go. So how is that going to work? Well, you can see that the pattern list already has a default, which is false, false, and true, true. And that if I apply that here, and I visualize these points now, you can see that false, false, left, true, true, stayed, false, false, left, true, stayed, and then etc., etc. So true means the points are going to stay, false means that the points are going to go. So what I need to do now is I need to create myself the pattern that I want for my calling. So as you can see here, it's in blocks of 2. In my case, it was for the bottom one, it was blocks of 1. So I want 1 out, 1 in, 1 out, 1 in, 1 false, 1 true, 1 false, 1 true. So I'm going to do this. I'm going to write here a panel, and then in the panel, I'm going to double click and I'm going to write false so that the first element goes, and then I'm going to type here true so that the second element stays. And that is going to be enough because this pattern is going to repeat over and over. When I plug this in here, I don't think it's going to work because since I have 2 lines in my panel, I need to make sure that the component knows that it's 2 different lines. That is basically a list of inputs. So the way I do that is by right-clicking here and making sure that this is not multi-line data, that is single-line data. And you can see how the panel immediately turns into a tiny list with a branch and zeros and ones, and now it's a collection of elements. I could add more here and blah, 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 but if I do that, it's going to give me an error, obviously. So I'm just going to double-click and remove all those lines. All right? And I'm also using a panel because I want to make sure that no one changes this. For me, it's important that this pattern has to be like this. So you can see how I had these points, and now after calling the list, what I have is only this point, and this point, which kind of matches what I wanted to do in my diagram. So I'm going to use the same technique to call the points that are on the top. All right, so I'm going to copy and paste this, and I'm going to plug the other list. However, and then I'm going to turn these points off. However, if I do that, you can see that I'm going to be calling the same points, and that if I look at them, I have the same ones. I don't have the triangulation that I want. And this is because for the other arch, I need to actually change the sequence, and instead of starting in false, I need to start with true, and vice versa. So this needs to go, and this needs to be here. And if I do that, you can see that now, if I turn this off, now I have been able to keep in the bottom these points, in the top the opposite ones, correct? And then, thankfully, I should be able to take a polyline and then just do, can I do a polyline between all these points and all these points here? But as you can see, it's not working. And it's not working. Why is it not working? When things are not working, what do we think is the most probable cause? It's probably a data problem. So as I typically suggest, can we first use a panel to take a look at what's happening here? If I take a look at this panel, I use this panel to see these are the first points. These are the ones on the bottom. These are the ones on the top. And then I'm going to create another panel where I'm going to replicate what is happening here. So I'm going to plug in the first one, and I'm going to shift add the other one. And you can see that what's happening is that the 4 points are added to the end of the list. And therefore, the polyline goes first through the 3 points on the bottom. So 1, 2, 3, you see that here. And then the polyline continues over the 4 points on the top. So polyline goes here and then continues the 1, 2, 3, and 4. So obviously this polyline is not going to work for my purposes. What I need to do is I need to figure out a way to mix this list with this list so that the resulting list has this element, the first one, this, the second one, this, the third one, this, the fourth one, fifth, sixth, seven, in a way that they are weaved into this pattern that does the internal triangulation. How am I going to do that? Well, we're going to see now in Grasshopper how to use weaving to put these two lists together into a one that has these elements woven. Weaving is an operation that can be found under list, and then these other components that we have not seen, but that I very much encourage you to check out and to give them a try. They're actually very useful. And weaving is a component that takes two sets of inputs, two lists, and combine them using a pattern. So using something very similar to the technique that we have used for culling. So what does that mean? So it means that, let's take a look at the component. The component says, can I use a pattern of input indices, so 0 and 1, 0 and 1, etc. And then here under 0 and 1, we have the streams of data that we want to mix. Okay? What does that mean? It means that here I have already a pattern that is zeros and ones. So what I'm going to do is I am going to plug in here my first one, my first list, the points that were on the bottom. And then I'm going to plug in here on the number one, the points that were on the top. And if I look at those now, you can see that the order of the points is a little different. And then, but they are all combined under the same list. So I can now plug this list into the polyline, and you can see that, oh, something is kind of happening. So I do have some kind of triangulation. It's not the ideal one. And I think what's happening is that input 0 is the one that has 3 points, so the ones on the bottom, and input 4 is the one that are on the top. So what I want to do perhaps is I want to define a triangle, a pattern that starts by taking points from list 1 and then keep going and taking points from the list 2, because I think that what I'm doing now is the opposite. So I'm taking points from 0 and then I'm taking points from 1. And that's why I start here, go here, 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 and then end up here. So I'm going to change the pattern. I'm going to say that I want you to take a point from list number 1, this one here. And then I want you to take an element from list number 0, so the one that you have here. And then I'm going to make sure that this is multi-line data. I'm going to plug this in here. And then, ta-da! It turns out that we now have the right triangulation here. And let me play around a little bit with this, see if it's actually working. So I have more spans, so you can see that I still have the gap. And here, as I retract this, I get more and more gaps on the side, which is kind of great, all the way to 0, which creates these weird overlaps here, which are not great. So yes, so 2, 3, 4, 5, whatever, you got it. This might be 4 now. This looks a bit more elegant. Okay, we are very close. So I'm just going to copy and paste everything for the right arts. So for the right arts, I would like to copy and paste all of this. So that's going to be, so that I have here for the top arch, now I have my points there, okay? And then here I'm going to create another polyline that is going to weave the points on the base, which are these ones, with the new points that I just created. So this one. And then I'm going to turn on that curve as well. Beautiful, beautiful. And let's not forget that I want to also create horizontal bars between the top members here. And that is actually going to be the easiest part, because I know that those points, I have them here, I have those points here, and I have them here. So what I can do is I can just create a line between 2 points between these ones and these ones here. And you can see that I now have the structure of the spatial truss. Wait. Are we done? Is this what we wanted? Yoo-hoo! Spatial truss! And with two curves and arches and blah, 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 and all the good things. This is actually very, very cool. But I think we can spice it up a little bit and make it a tiny bit cooler. Just for the sake of visualization, I'm going to indulge a little bit in adding pipes to kind of see like the thicknesses of, to kind of see like these elements with a little bit of thickness and perhaps do some renderings. So I'm going to go to surface, I'm going to do pipe, and then I'm going to place a pipe on, first I'm going to place pipes on the curves. So the actual curves. So this is going to be the base arch, the top arch, and the right arch, and the radius is going to be something that I'm going to control numerically. So the radius is going to be something very small, like this. Okay? So that's going to be one thing. And then I probably, well, that's actually quite small. And then for the, so that's going to be one thing. Those are going to be one pipes. Then for the horizontal bars, I'm also going to do pipes. I'm going to copy and paste this, and I'm going to overlap it with this. I'm going to make them a little smaller. So I'm just going to do a slider that is start at 0.1 and yeah, something like this, much smaller. And then for the polylines, because they have angles, and if I do pipes, the angle of the pipes are going to overlap with the other ones, I'm going to actually explode these polylines into single segments so that the pipes have a clear start and a clear end. So I'm going to go here, I'm going to utilities, I'm going to go to explode, and as I do explode, you can see that the result is that I have, for this polyline, I have like a bunch of line-like curves, and for this one, I have the same, and then I can pipe this, I can add these guys to this rendering, for example, and then you can see how now the pipes have been rendered as part of, and then if I do some render visualization, for example, so let me bake this, and let me bake this. You can see that now it looks a little sexier, right? These pipes with some thickness, etc. That kind of looks pretty cool, as I may have to say. Not because I made it, but I think it's kind of cool. And last but not least, should we try the same thing that we tried before in the previous exercise, where we took all these curves and then we used them as the support for all this network of trusses? Let's do that. So I'm going to bring those curves here, 1 and 2. I'm going to set one curve here. I'm going to set the other one curve here. I'm going to divide the curve by a control amount of points. So for example, 20. And then I'm going to do the same for the other one. I am going to graft these outputs. Remember, I don't really like grafting outputs like this, but just for the sake of speed. And then, are we ready for this? This is going to be seriously cool. So we're going to add that here. We're going to add that here. And then, if I now bake all of this, you can see that, well, I can see that I can turn a lot of things off here and off here, a lot of points, and then I can see this network of, you can see this network of arches, and with a bigger depth and a little bit of this. And then you can see how now, you can see how they now look like a canopy, like a structural canopy of elements. And actually kind of loft. What are the base arches? Can I flatten these and loft a curve through them? I can. Choo-choo! And so, and then if I bake this surface and I bake all these pipes here and I group them, and I bake all these pipes here and I group them, then I get my result is going to be something like this. Choo-hoo! Nice! Woohoo! How do we like this? This could go. This is a very nice parametric definition of some pavilion with some structure and like a little bit of structural logic, a tiny bit of optimization. These members are smaller, these members are bigger, etc., etc. And I can look. Wait. Ooh. Whoa. Okay. And I think with this, I think I'm done for the day probably. All right. Hopefully you liked this exercise. Maybe it was a little long, but I think we learned a lot of things. On the way, I think we learned very interesting techniques. I think we got to see how data manipulation and smart data matching can be a really strong asset in our definitions and allow us to do really powerful parametric modeling like the one that you just saw here. So with that, I am going to leave it here. I would like to thank everyone who has joined me recording this tutorial in the live streams that we do. Thank you very much. And if you liked what you saw, if you think you learned something from this video, maybe consider liking the video or subscribing to the channel, and maybe even turning on notifications so that you know when we publish new stuff. Crazy, right? But in the meantime, thank you very much, and I will see you on the next videos on this series, where I think we're going to keep doing more exercises, because these exercises are cool. I think they're a lot of fun. Thank you very much, and see you in the next videos. Bye bye.